Okay, so here's our second part to the review. Um, Now we're going to do what we call the torque problem. We're looking at a ring. It's more of a hoop than a ring. Whether you call it a hoop or a thick ring doesn't really matter, but it says it has a mass of 0.8 kilograms and a diameter of 45 centimeters. It says it has a hole in the middle and it's 12 centimeters wide. And starting at rest, the ring achieves a rate of rotation of 30 RPMs in 4 seconds. So here's our ring. Notice a couple things. There's the radius of the empty space, and there's also the radius of the ring. The radius of the empty space, once again, you watch out for centimeters and diameters, so it comes out to be 0.06. We'll call that R1. Then we have the radius from the middle of the ring to the outside, which is R2, which we'll call 0.225. So that's R2. So we have R1 and R2. Both need to be in meters, which I did. I converted. And now I'm ready to find what we call the moment of inertia. So a thick ring really does have the hardest equation for moment of inertia. So the thick ring's moment of inertia is 1/2 the mass times the interior radius squared plus the exterior radius squared. And so for our mass, if you come up here to the top, you'll see that it's 0.8. And we can put that in right here. So we get 1/2 of 0.8 times R1. Doesn't matter who's R1 or R2. I'll just put 0.06 in here. Remember to square it. And then 0.225, and you got to square that as well. And so that's the first part. You plug all that in, and we get a moment of inertia equal to 0.021. On the quiz tomorrow, you're going to have to know these units. So it's kilogram times meter squared. Think of the location of the mass. Mass times area. Remember, whenever a disc and a hoop roll down a hill, every time the disc will win, as long as their masses are equal. So now we're ready to calculate what W would be at 30 RPMs. To do this is just another conversion. It's like comparing miles per hour to kilometers per hour. It's two ways to look at the same thing. They're both W, but we need to get our rotations per minute into a more user-friendly kind of thing, radians per second. So to do this, we can turn rotations to radians. We know that 2 pi radians is equal to 1 rotation. Go back the other way then, and we take care of the minutes. We want to go to seconds, and so we do that, and we can then say 1 minute is 60. So it looks like we need to multiply by 2 pi and then divide by 60. And so when we do that, we get 3.14 radians per second. Then we're ready to calculate alpha. Now remember, this started at rest, so that means that our W initial is 0. So we can then plug in W final, which we said was 3.14. So really, if it takes 4 seconds to get this thing started, it's as simple as saying 3.14 force, or that turns out to be 0.785 radians per second squared. So now we get down to kind of the crux of the problem here, or what really makes this thing work, and that's torque. So torque equals two things. That creates a lot of problem for us. Really haven't had too many things that equal two things this year. But torque equals force times radius, and it equals moment of inertia times angular acceleration. So what we're really looking for is the force. Now to get to the force, we're going to have to take our two previous answers, moment of inertia and angular acceleration, and multiply them together. And when we do that, we actually calculate the torque. The question is not really asking for the torque, but the torque is 0.016 Newton times meter. What the question wants is the force. So now we just have to divide by the radius. Now if you take a look at this picture, I put a little force vector in here, and you can see it's acting on the outside radius. So we're going to have to use that 0.225 number. So I'm going to put that in right here in meters for the radius. So we get a fraction again, 0.16 divided by 0.225, and you can see that the force is pretty small. It's just 0.071 newtons. And so that's what's going to go here in this blank, 0.071. So you would think you'd be pretty much done, but you're not, and that's the bad news, because this last question is going to force us to do the whole thing just backwards. So in the first one, we supplied less than 1/10 of a newton of force, and in return we got 30 RPMs. So now we're going to really pump it up. We're going to pump it up to 5 newtons. So if we have 5 newtons and we apply it to the same ring, so we're going to have the same radius, 0.225, we get a new number for our torque. So if we calculate the torque, you would get for a torque 1.125 Newton meter. That's not what we want. We want to get to RPMs. So then we realize that torque also equals something else, I times alpha. So we're talking about the same ring here, so it still has an I of 0.021. Put in the torque, 0.1125. We have alpha then, what we can solve for. When you do this, you figure out that it has an alpha equal to 53.37 radians per second squared. So now that we know what alpha is, we can use that. Remember, we started at rest, so this is like saying W final over T. There was no W initial because it was just 0, and the T, once again, just as before, was 4 seconds. So we take 53 and we multiply by 4, and we end up with our W. So W at this point is around 214. Now, depending on how you round it on some of these things, you might get a slightly different answer, which is okay. There's quite a bit of room for error here, or room for rounding, really. And we're going to take this and we're going to turn it into RPMs. So normally, we multiply by 2 pi and divide by 60. So this time we're going to divide by quantity 2 pi. Now, if you don't put it in your calculator as quantity, you will miss it. And you have to multiply, by 60, and we end up with something. I'm just going to put an about because we could round so differently here. Around 2,000 RPMs. With, a certain amount of uncertainty due to rounding of maybe 100. So, go ahead and give it a shot and see how you do, and hopefully everything will work out for you. Study hard, and we'll see you later.